Okay, I guess it's about time. I guess we can get started if there are no questions or anything unusual. So today I'd like to continue with the discussion of reciprocity theorem. Dr. Na has discussed that with you. I'm just going to pick off from where he has ended. Okay, so reciprocity theorem is something that is very important in my opinion, and also very beautiful, and is very similar to human relationship. This is something that Confucius said many years ago. It seems that Jesus Christ also said the same thing about 2,000 years ago, which is that don't do unto others that you don't like others to do unto you. You can find this in the Bible. You can also find this in Confucius' teaching. Okay, and this is essentially what reciprocity theorem is. So I'm going to discuss reciprocity theorem. It is a mathematical way of stipulating the relationship between two groups of sources. Okay, so if you have say two groups of sources, and then you can actually have that sources being turned on and off. So what you do in the experiment is that you first assume that you have a scatterer. Okay, the scatterer can be quite complicated. It could be anisotropic and homogeneous. And then if you put some sources next to it, like J1, and then M1, and you will produce a set of fields which are called H1 and E1. Okay, this is experiment 1. And then in experiment 2, you will do the same experiment with the same source. Okay, I'm not drawing the object or the scatterer very precisely, but these two are supposed to be the same object. And usually J1 is denoted by that, but the M sources are denoted by usually by a double arrow. Okay, at least there's a convention in electromagnetics. So in the second experiment, you would put the sources J2 and then M2 next to the same object. And then you will have a set of field H2 and E2 produced. And you can say something about the relationship between these two field quantities. The first one has been derived by Dr. Na, so I just tell you the result. Okay, so if you actually look at these two fields, you can write down the relationship that the surface integral of E1 crossing with H2. So these are not pointing vectors. Kind of a strange cross product, but these two cross products are supposed to be taken over two different experiments. You take E1 from experiment 1. Let me see, you can make this bigger so that you can see it better. Okay, so you take E1 from experiment 1, cross with H2 from experiment 2, and then do the same with E2 from experiment 2. Okay, let me call this experiment 2. Okay, you take E2 from experiment 2, crossing with H1 for experiment 1, and then you do all these cross products and integrate over the closed surface S. And you can show that they integrate to 0, provided that the surface S contains no source. Okay, no source inside. All the sources are outside this surface S. So this is a remarkable thing, because you can use this to solve some problems sometimes. I will not tell you how to use this at this point, but just to tell you the fact that this is a useful theorem. And this is called the Lorentz Reciprocity Theorem. Okay. The second one, which is called the Reaction Reciprocity Theorem, is more useful, in my opinion. And what it says is that if you now study this same derivation, but with the sources M and J inside the closed surface S, okay, so if you were to put all the sources inside now, what you find is that you can come up with this relationship. And again, I do the experiment 2 times, one with M1, J1, and then I do the second experiment with M2, J2. This should be, M should look like that, and then J should look like that, okay? And then you can come up with this relationship that says that the volume integral of these sources, when you dot product them, like you take the electric field from experiment 2 and dot with J1, and then you take the field, the magnetic field from experiment 2, dot with the source from experiment 1, and then this should be equal to the opposite experiment. You take the field from experiment 1, dot with J2, and then H1 dot with M2, I think. Okay. So this is called a reaction. This kind of integral is called a reaction, because and you can also introduce a shorthand notation that whenever you dot product to integral, you replace that with this notation, which is called an inner product, a reaction inner product. This is usually called a reaction inner product. Okay, and then the above reciprocity theorem can be written as E2 comma J1. That is just this inner product here, minus H2 comma M1 should be equal to the right-hand side, okay? And if I write the right-hand side in this compact notation, it would be E1 comma J2 minus H1 comma M2, okay? So this is the reaction reciprocity theorem, because we are calculating these quantities. These quantities are called reactions. Okay, let me draw a line here to not get you confused. Okay, so this is reaction reciprocity theorem, and sometimes it's also called the Ramsey reaction theorem. Okay, so this is kind of surprising because you are doing the experiment 2 times separately, and yet you have this wonderful relationship between the currents and the fields generated by these 2 experiments. Okay, the inner product here actually is something that is very similar to the inner product in matrix theory, because when you multiply 2 functions and integrate, say in 1D, this is 1D, it's easy to see in 1D, and you can convert it into something that is like delta x f of I delta x. If we were to do this numerically, you will convert this into summations. I is equal to 1 to n. So this is like taking a vector f sub I dotting with g sub I, and then multiplying them together. You can define your f of I to be square root of delta x, f of I delta x, for instance. And then you can define your g sub I to be square root of delta x, g of I delta x. And then you can convert this into something, and this is just a matrix inner product. So this is for 1D integral. You can repeat this for 2D integral and 3D integrals. So essentially what I'm trying to tell you is that this inner product expressed in terms of an integral, like this one over here, okay, this inner product is very similar to the matrix inner product between two vectors. I said that the vectors now is infinite dimensional because when you make delta x very, very small, these vectors are infinite dimensional vectors essentially, okay? So this actually is a very important theorem because what is the physical meaning of this? And to make the physical interpretation easier, we can make m equal to 0. Okay, we take away the magnetic current, then the reciprocity theorem just says that V1, comma J1 is equal to dV E2 should be E2, comma J1, E1, comma J1, J2. Okay, so the reciprocity theorem just say this. You can think of this as a kind of a measurement. So what you're trying to do actually to measure the field E2 with the current J1, and here you try to measure the field E1 with the current J2. Okay, and it becomes more obvious if J1 is a Hertzian dipole. If J1 is a Hertzian dipole, then it would be something like I1 L1 delta R minus R1. So you can write a Hertzian dipole current to be that way. And then you can also write a Hertzian dipole to be something like pointing in the L2 hat direction I2 L2 delta R minus R2. So if you assume Hertzian dipoles in this experiment, then the first expression that you have becomes L1 hat I1 L1 E2 dot with R being evaluated at R1, and then dot with there's a dot product over here. So if you plug this in, the left-hand side will evaluate to that, and then the right-hand side will evaluate to something like L2 hat I2 L2 dot E1 R2. Okay. So you can see that this is like a measurement of the field E2 at location R1, and the right-hand side is like the measurement of the electric field at location R2. And reciprocity theorem says that these two measurements should be equal to 0, not 0, should be equal to each other, okay? So it's like, if you measure me, it's the same as me measuring you. You have these two systems working in a reciprocal fashion, okay? And of course, the requirement for reciprocity is that mu equal to mu transpose, and then epsilon equal to epsilon transpose. If a medium satisfies this kind of relationship, then the medium can be proved to be reciprocal, okay? So this is a very important theorem because we can use that to study interaction between two antennas. Say if we have two antennas, as we say here, let me see if I can move this down slightly. And these two antennas are radiating in a very complicated terrain. Let me shrink this. Okay, these two antennas are radiating in a very complicated terrain. Let's assume that the inhomogeneous medium, the very complicated medium that I talked about in the previous slide, this mu and epsilon, that they can be shaped in such a fashion that they will be like these two experiments over here. Okay, let me see, why is it not scrolling? It's refusing to scroll now. My screen is frozen for some reason. I don't know why. Well, let me try something. I usually try to do this when my screen is frozen. I go to the task manager. And when I run the task manager, then it usually unfreeze my screen. Yeah, that it works. Okay. So when I just run the task manager, then my screen unfreeze itself. So what I'm trying to say is that if we have these two problems over here, and this terrain is very complicated with two antennas, but the medium that I have in proving this reciprocity theorem is quite arbitrary. Okay, mu can be conductive, epsilon can be conductive, or mu can be lossy. So you can actually shape this into anything that you want. Let's imagine that we have shaped this mu and epsilon into something that looks like that, so that it looks like an antenna experiment. Then I can perform these two experiments. That is, I put a Hertzian dipole here to excite antenna 1, and then I put a Hertzian dipole to excite antenna 2. And these two dipoles are very, very small, so that when I excite those two antennas, I can essentially think of that the input port of this antenna, these are like input ports of the antenna, they are so small that you can apply circuit theory here. Okay, and then you can apply circuit theory here. And then you can write a linear relationship between the current J1 and V1 and the current J2 and V2. Say if you have an input port here, you will have a voltage V1 and V2 here. You would be able to write a relationship between V1, V2 and the current I1 and I2, okay, Z21, Z22. This will be I1, I2. For two reasons. For the reasons that I'm putting myself so small when I'm in the transmit port of this antenna that I'm in the regime where I can apply circuit theory. You remember that we went through the exercise that if you're in dimensions that are very, very small, you can apply electrostatic theory and magnetostatic theory. Apply those theory in the vicinity of this port. And also, if I have J1 or I1 at this port, and then J2 or I2 at this port, and V1 and V2, this is a linear system. Okay, so this is a linear system. In the most general way to relate a linear system, you can go and test this out for yourself, okay? That if V1 and V2 are linearly related to I1 and I2, you can test linearity. The only way to relate them is through a matrix like this. This is a general way to relate these two variables so that the system is linear. You can actually go through the test of linearity quite easily. So that means that I can reduce this analysis of this system into just a matrix system like this that you have encountered before in matrix theory or in circuit theory. Okay, this is called the impedance matrix, which means that I can apply circuit concepts to this problem irrespective of how far the two antennas are apart and how big the terrain is, as long as it's a linear system, as long as when I'm doing the measurements at these two ports, I'm in the quasi-static regime so that circuit theory can apply, okay? So if that is the case, then we can actually imagine that we can do this experiment now. We can replace this picture with this picture over here, okay, where I just put a black box to represent this very complicated structure, and there should be an impedance matrix associated with this black box. Okay, that impedance matrix is this impedance matrix over here. And then reciprocity should hold here, which means that if I now turn on J1 and look at the field E2, and then turn on the current J2 and look at the field E1, this relationship should apply. If I do these two experiments consecutively, the first experiment is to turn this on and turn this off. Okay, the second experiment is to turn this on and turn this off. And the first experiment will generate E1, okay, over here. The first experiment, if you turn J1 on and J2 off, it will generate E1 over here. Okay, the second experiment, you turn J2 on and then you turn J1 off, and then it will generate E2 over here. Okay, so you can calculate this reaction, this inner product, which is also called a reaction between the current and the field, and the two should be equal by reciprocity theorem. Okay, so let's calculate this more carefully. Let's look at what E2, J1 is. E2, J1 would be equal to the volume integration of E2 dot with J1. Okay, since I'm only calculating this inner product over J1, J1 is assumed to be an impressed current source. And it's only going to be non-zero over here, okay, since it's a current that you put in space and you cannot change its value. That's the meaning of an impressed current source. Its value would not change once you put it into its place. It will just produce a field to interact with the environment. So I need to calculate this quantity. And I know that if I'm in the quasi-static regime, this current is a constant on this length of this wire, because that actually is what happened. If you start driving this with the current source, you will find that the current is a constant on this wire. You can assume that current to be J1, okay? Then you can assume that J1 is of the form of, say, the current flowing in the length of the wire, I1, divided by A. Okay, J1 has the unit of amperes per meter square, so it can be written as something that flows in this direction. And then I can say that the L hat is something that points in that direction. And if I plug that in there, dV, okay, dV is just A dl for this wire, because it has a cross section of A, and dl is in that direction, and hence this integral now becomes, if I plug this in here and plug this in here, this integral now becomes I1, okay, E2 dot dl from A to B, okay, from A to B on port 1, from A to B here, okay. I just take the constant current I1 out because I1 is independent of position. And now if I integrate this over the port I1, this should be equal to I1 times the voltage minus the voltage of port 1, okay, the voltage at this point. And that I will call an open circuit voltage. Because when I do this experiment, when I turn on J2, I'm assuming J1 is turned off. So in the place of J1, there's no current flowing. There's just an open circuit there. But an electric field E2 will be generated at this point, J1, or this port 1. And that electric field produces a voltage. Okay, assuming that there's no current there. But this voltage is a voltage when port 1 is open circuited. So usually we call this the open circuit voltage at port 1. Okay, everybody gets that? Any questions on this derivation? The E2 comma J1, the inner product between E2 comma J1 is just I1 times V1 open circuit. Okay, then I do the experiment on the right-hand side. The experiment on the right-hand side is I turn off J2, I turn on J1. Okay, so I need to calculate E1 comma J2. Okay, again, I would have this inner product that I need to calculate. And I can go through the same argument as before. This will be I2 E1 dot DL. Maybe something like C to D on port 2. Okay, so this will be minus I2 B2 open circuit. Okay, B2 open circuit. Everybody get that? So what happens is that I'm going to derive some very useful formula. Reciprocity theorem says that these two quantities should be the same. I1 V1 open circuit should be I2 V2 open circuit. Okay, that's what reciprocity says. But I also have a matrix theory description of this by this, what we call the circuit impedance matrix, Z11, Z12, Z21, Z22. Okay, I1, I2. So how do I find V1 open circuit? And how do I find V2 open circuit? Well, this is a simple circuit theory. So you have a two-port network. This is V1, V2, and then this is I1, I2. Okay, and then you have this very simple circuit relationship. In order to find V1 open circuit, what we need to do is to make I1 equal to 0. And then V2 not equal to 0. Okay, you essentially put the voltage source on port 2 and measure V1 in port 1. And what do you get? Okay, when you do that, then V1 open circuit would be the case when I1 is equal to 0. Okay, I1 is equal to 0. So you multiply this out, it would be Z1 I2. Z1 to I2. Okay, and then similarly, you can show that V2 open circuit is the same experiment where you actually let I2 be 0, and then V1 is not equal to 0. And then if you go to this simple relationship again, is Z21 I1. Okay, so V1 open circuit is given by that, and V2 open circuit is given by that from circuit theory. And from that thing, we plug in what we have derived before. We have derived this using reciprocity theorem. Okay, so if you plug this in the above equation, now you have I1 Z1 to I2 should be equal to I2 Z21 I1. This implies that Z12 must be equal to Z21. This is probably something that you have studied before or learned about before. That is, in a reciprocal circuit, the impedance matrix is symmetric. This means that the impedance matrix Z, which is Z11, Z12, Z21, Z22, is a symmetric matrix. Okay, how many of you have come across this before in your undergraduate course of circuit theory? or is this new to you, that an impedance matrix is symmetric for reciprocal circuits? Is this new or is this not new?
I've came across this before.
Okay, very good. You have come across this before then. So this is not completely new to you, which is good, okay, which is wonderful to know. And this is just a proof from electromagnetic theory using the reaction reciprocity theorem. And with this thing and going through very simple circuit arguments, you can prove that this impedance matrix is symmetric. And in general, you can extend this to something even more general. That is that if you have a impedance matrix in circuit theory, you generally have very big impedance matrix like this, and then Z21, Z2, 3, 1, and so on, and then Zn1. And then you have this Znn. And Z is equal to Z transpose if circuit is reciprocal. Okay, if circuit is reciprocal and essentially the two are in agreement, the two would be in agreement. Okay, so if there are no questions about this, what this says is that if you design an antenna system between the transmitter and the receiver, they are actually cross-coupled with this Z12 and Z21, which means that if you can receive wow, if you have this to transmit and if antenna 2 receive wow, it also means the other way around. That is, if this is acting as a transmitter, this is acting like a receiver, because Z12 and Z21 are equal to each other. If something transmits wow between the two antennas, they also receive wow between the two transmitters, is what it means. It's like a tit for tat kind of relationship. Okay. So there's another thing that you can prove using reciprocity, which is that the radiation pattern and the receiving pattern of an antenna is the same. If an antenna transmits wow, it also receives wow. Okay, and that can be proved from reciprocity theorem. And also, we have a reciprocal medium if epsilon is epsilon transpose. If mu is equal to mu transpose. Okay, could you think of any media that you have studied before that does not satisfy this relationship? We have studied quite a few media, and they like to bring you to the attention of the gyrotropic medium. And if you have a gyrotropic medium, say, I think we derived that before, epsilon is something like epsilon 1 jg, or maybe I can use j epsilon g minus j epsilon g epsilon 2 0 0 0 0 epsilon 3. I think we went through lectures and derived this permittivity tensor for a gyrotropic medium. Is this medium reciprocal? If you now do a test of reciprocal medium on this gyrotropic medium, is it reciprocal? Anybody wants to do the test in his mind and see if this is a reciprocal medium?
Yes, it is. First.
What?
Yes, it is at first sight.
Yes.
Well, is this a symmetric matrix? Because this means that all the tensors are symmetric.
Oh, it's not dagger, it's transposition. Okay, I see it. Then
they're not symmetric. So a gyrotropic medium is not a reciprocal medium. Okay, this is something very important to remember. Is this gyrotropic medium lossless? Is this a lossless medium? Remember, this is the condition for reciprocity. For losslessness is this other condition. This is the conjugate transpose.
It is lossless.
Yes, it's lossless. So a gyrotropic medium is lossless, but not reciprocal. Okay. Whereas most media that we have in this world is not gyrotropic, so they are symmetric and reciprocal. Okay. So it's quite easy to find reciprocal medium, but it's not easy to find gyrotropic medium. You find gyrotropic medium in the ionosphere. Another place that you can find it is in ferrite. Okay, so if you have a ferrite rod, for instance, if you bias it with the magnetic field B, the spin in the ferrite interacts with the magnetic field in such a way that they produce a gyrotropic medium. And what that does is that the wave is not traveling symmetrically in two different directions. Okay, the tit-for-tat relationship doesn't hold anymore. So if you put a ferrite rod in a waveguide, and you might want to bias it with a magnetic field, okay, maybe a B field like this. And then when the wave propagates in this direction, it does not propagate the same manner as the wave propagating in that direction. So using this kind of ferrite rod, you can make non-reciprocal medium. Okay, and those are useful in electronic devices. If things don't propagate symmetrically, you can make isolators out of them. Isolators means that the wave can propagate one way, but the wave cannot propagate in the other way. But luckily, most media that we have are reciprocal. So if you have two antennas, and if this antenna can talk to this antenna while, the same antenna would be able to talk to the other antenna while, okay? And I'm not going to prove this in great detail, okay? But it's proof in the lecture notes that you can actually write the radiation of an antenna as being equal to the total power over 4 pi r squared times the gain function. Okay, that we have learned before. And gain function is a function that tells you how the antenna radiates. Say if a function looks like this. It says that this antenna is radiating predominantly in certain direction. This is a function of angle, okay? And then you can also use a concept that the power received by the antenna is the incident power times the effective aperture. Okay. So if this is a transmitter, this is a receiver, then there is actually an effective aperture associated with that receiving antenna, and the power received in the antenna is given by this incident power. This incident power can be coming from here, like when the radiation power leaves this thing, and by the time it reaches the antenna, it can be used or be looked upon as an instant power, and then you can find the power received, okay, using this formula. And using this kind of argument, you can actually see that the transmit and the receive pattern of an antenna are the same. If an antenna transmits well, it also receives well, okay? And with this kind of argument, you can actually show that the aperture is a function of angle, because depending on how you arrange your antenna, okay, depending on how you orient the receive antenna, its effective aperture will be different. For instance, if you orient your receive antenna so that it doesn't face the transmit antenna, then its effective aperture will be small. Okay, so with this kind of argument, you can actually show that the effective aperture, okay, divided by the gain function is actually a constant. And that constant is lambda squared over 4 pi. Okay, I will not derive it, but it's derived on the lecture note. Okay, sort of derived in the lecture note. And actually these are the same. Okay, this has to be the same. The same antenna is used for transmit and receive. So these two angles are the same. And that turns out to be a constant. Okay, and this relationship is derived in the lecture note, but not completely. I also refer to Kong's book to derive this relationship. Okay, so it's not entirely written in the lecture note, but you should know this relationship. Wow. Okay. So are there any questions regarding this effective aperture concept? Effective aperture concept is essentially the concept that if you have incident plane wave expressed in this manner, that plane wave multiplied by this effective aperture give you the power received. Okay, and then the gain function is essentially a function that tells you how the powers are oriented to different direction or radiated to the different direction of the transmit antenna. You can show that for an antenna, if it's been used both as a receiver and a transmitter, this ratio is always a constant. And that constant is lambda squared over 4 pi. Okay. There's one other thing I like to discuss before I move on. If you don't have any questions on this, okay. I'd like to discuss one other fact before I move on. I like to discuss the fact that the concept of reciprocity is very much related to the concept of a symmetric matrix system. Say if I have a matrix system AX is equal to B, and if I do experiments 2 times with this matrix system, I excite the right-hand side with the vector B1, and then it gets solution X1. And then I do the second experiment, okay? Excite the right-hand side of this matrix system with B2, and then I get solution X2. But now if I take this equation and multiply by X2 transpose, and take this equation and multiply by X1 transpose, okay? Then essentially, X2 transpose dot A dot X1 is equal to X1 transpose dot A dot X2. Are they equal to each other? When would the left-hand side of these two equations be equal to each other? Anybody wants to suggest a relationship that will make the left-hand side of these two equations equal to each other? I have a matrix system equation that I can write like this. I do 2 experiments with the matrix system. I multiply the first equation by X2, and then I multiply the second equation by X1. And now if I stare at the right-hand side, are they equal to each other? If not, when would they be equal to each other? When would this quantity be equal to this quantity? Anybody good in linear algebra and can tell me the answer? Anybody? What happens? What is this quantity? Is this quantity a scalar or a vector? Anybody?
Scalar.
A scalar. Okay, good. If it's a scalar, if you take its transpose, what does a scalar become?
The same here is the same thing.
Very good. Okay, very good. So I can actually take this number, which is a scalar, and take its transpose. And you know that there's a very simple linear algebra rule that if you take a transpose of the product of 3 matrices, it's actually the transpose of this times that. right? This is a rule that you should know in linear algebra. That is, if you have three matrices A, B, C, if you take its transpose, it's like C transpose dot B transpose dot A transpose. Okay, it's something that you should learn. So if I apply that rule, I have that. And then these two will be equal to each other. Okay, because this is itself. If I take the transpose of a scalar, it's itself. So this thing will be equal to that thing if A transpose equal to A. Okay, so if A transpose equal to A, then left-hand side equal right-hand side. So if the matrix system is symmetric, then left-hand side equals right-hand side. And from this equation, I will get x2 transpose dot b1 is equal to x1 transpose dot b2. I'm now just equating the right-hand side. Okay, because I already proved to you that the left-hand side are equal to each other if A is symmetric. If A is symmetric, then the left-hand side equal to each other. This must be true. This is the linear algebra way of stating the reciprocity theorem. I can think of B1 and B2 as sources, X1 and X2 as field. So I'm measuring the field X2 with the source B1, and that should be the same as measuring the field X1 with B2. And if the matrix system is symmetric, these two measurements should be the same. That's essentially the gist of reciprocity theorem expressed in terms of linear algebra. But of course, when you write it in terms of Maxwell's equations, it's rather complicated. But if you look at from the linear algebra viewpoint, it actually is quite simple. Okay, any questions on this? If not, then I will move on to something else. I like to move on to equivalence theorem. Okay, I like to actually move on to this topic here, talking about equivalence theorem or equivalence principle, and I'll do different cases, inside out, case, outside in, case, general case, and then if I have the chance, I talk about Huygens principle as well. Okay, so let me look at this case over here, okay, which is actually the inside out case. So this is the inside out case. Okay, so I have a problem on the left-hand side where I have some sources J and M, okay? And I'd like to replace the problem on the left-hand side with an equivalence problem. So that outside, the two problems are the same. But inside of the case on the right-hand side, the field is 0. How can I do that? How can I achieve that? Okay, let me see if I can put this away. Let me put it down here. Okay. So how can I achieve the two and make them to be the same? Well, the right-hand side, if I were to do that, if I make the outside field the same as the problem on the left-hand side, and I make the field inside to be 0, that is not possible because the field will have a jump discontinuity across this surface S. But I can remedy that by putting surface current sheets on this surface. If I impose the current sheets in such a manner that Js is n cross h, ms is e cross n, I know what the jump conditions for h and e are. If there's a jump in the field, tangential E has to satisfy this jump condition. Tangential H has to satisfy this jump condition. And if these jump conditions are satisfied, then the electric field will be 0 inside. Okay, so this is like what the German call the Gedanken experiment. Or thought experiment. Okay, this is the German word for thought. Okay, so if you think about this, the field is 0 over here, but the field is not 0 over there. But E and H are the same in both cases. The only way that the right-hand side could be a solution to Maxwell's equations is that you have to put in surface current sheets. And if the surface current sheets are chosen appropriately, then you will cause the field to satisfy this jump condition. Okay, will satisfy this jump condition. And then by uniqueness principle, okay, these are the only possible solutions that you can have on the right-hand side. Is this clear? These are all physical arguments. This is called the inside-out problem. Any questions on this? So problem A is equivalent to problem B. The problem B, we put some equivalent sources on the surface S, okay? Then we do the outside-in case. We did the inside-out case. We do the outside-in case. Now we assume that we have some sources outside this surface S, okay? This source produce field EI, HI inside this surface S. And I like to find equivalent problems on the right-hand side so that the fields are equivalent to each other inside this surface S, okay, EI, HI. But in the second problem, the field outside is 0, okay? The field outside is 0, and again, I can invoke the jump condition. The only way that this can be satisfied, or this right-hand side problem can satisfy Maxwell's equations, is to put in surface currents. The surface currents will produce the jump condition necessary to make the field outside 0 and the field inside not 0. And hence, the problem B is equivalent to the problem A inside this surface. Okay, I call this the outside-in problem. Okay. Okay. The fact that I have 0 field inside, this is also called the extinction theorem. Okay. The fact that I have 0 field outside, this is also called the extinction theorem. Okay, so any questions on this? The structure on the right-hand side must satisfy Maxwell's equations because it satisfies all the requisite boundary conditions. Okay, and because it satisfies all the requisite boundary conditions, by the uniqueness theorem, the field inside must be the same as each other. Okay, and then I will have a general case. The general case is where the field outside is not 0, the field inside is not 0, then it will be just a combination of these two cases I had before. Okay, if I add inside out case, okay, inside out case where the field inside is 0, and then add the outside in case. And if I linear superpose the two problems by principle of linear superposition, can add this problem to generate any outside field that I want and any inside field that I want. And this gives me the general case. So the general case is that if I stipulate some field inside the surface S, if I stipulate some field outside the surface S, then if I put this kind of surface currents on the surface S separating these two problems, then the jump conditions are satisfied correctly, and this solution must now be Maxwellian. Okay. When a solution satisfies Maxwell's equation, we call it a Maxwellian solution. Okay. Are there any questions on this? If not, then we go to a case, do another Duncan experiment. Okay, we do another Duncan experiment. You go back to this problem that we have initially, this inside out case. And inside out case, the inside is 0. There's no field inside. Okay, there's no field inside. So I can start out with a problem where I have JS is equal to N cross H. And then I have MS is equal to E cross N. And then I have E equal to 0, H equal to 0 on the, okay, I have this equivalent, let me say that this is the equivalent surface. Let's assume that this surface is equivalent. So I put a dotted line over here. I put JS on it. I put MS on it. Okay. I cause the field to be 0 inside, but non-zero outside. So outside it will have E and H. Inside will be 0. Now, since the field is 0 inside, it doesn't hurt if I put an object in there. Agree? If I put an object inside, the field outside will not change. Do you agree on that, since the field is 0 in there? Everybody agrees? Maybe I should ask, do you have any questions on this problem? The fact that you're not answering my question bothers me. Okay. Does it make sense that they put this thing inside, nothing changes?
Yes, that makes sense.
Okay, makes sense. Very good. I can also put a PEC object inside. The thing wouldn't change, right? Now we slowly make this PEC object bigger and bigger until it feels the whole of the inside of this surface S. Okay, this is the surface S, where the equivalent surface S is. Okay. Then nothing would change. Do you think so? Nothing happens. But now I'm going to invoke a principle that can be proved very easily. A electric current source next to a PEC cannot radiate. Only this other current source can radiate. Okay. An electric current source next to a PEC cannot radiate. And how can I see that? Let me see if we can prove that quite easily. Okay, let me prove that. Okay, say if I have an electric current source, this is a PEC. Then on the PEC, the boundary condition is that N cross E must be 0. Okay, and then if I put a current sheet J very close to the PEC, and let me call this JS. Okay, and then I have another current called J test outside. Okay, so when I do experiment 1, I use reciprocity theorem to do these 2 experiments consecutively. The first experiment, I turn JT on and turn JS off. And then I would have N cross ET to be 0. Agree if I do experiment 1, okay, with JT on, JS off, okay? Now, if I do the experiment second time around with JT off, JS on, okay? And if I calculate the 2 reactions, it will be JET cross JNs must be ES. Let me call this ES, okay? The ES, this will produce ES comma JT. These 2 must be equal to each other by reciprocity theorem. But N cross ET is equal to 0. And right on JS, this must be equal to 0. Okay, left-hand side is equal to 0. Does this make sense? Because tangential E is equal to 0. Those reaction between ET and JS is equal to 0. JS is a surface current. Because JS is a surface current, left-hand side is 0 because tangential E is equal to 0, which means that if JS produces an ES over here, okay, the right-hand side should also always be 0. Okay, which means that if this is true for all JT, arbitrary JT, it means that ES must be 0. Okay, so this equation can only be satisfied if ES is equal to 0, which means that a surface current on top of a PEC cannot produce an electric field outside. Okay, does this make sense? A surface current put on top of a PEC cannot radiate. Okay, so we go back to this problem then. then this surface current, which is next to a PEC, cannot radiate. The only thing that can radiate is this one. Okay, the only thing that's radiate is this one. So we can remove this current and say that this is redundant, it's useless, it's not going to radiate anyhow. Why don't they just take it away? And then you can say that I can actually put this MS on here and it will be the only radiating current. Okay, any questions on this? So the equivalence problem can be reduced to just impressing a magnetic current sheet on a PEC surface. This problem will produce the same equivalent field, E and H outside. Okay. And you can do the same Gedanken experiment with PMC now. Okay. In the PMC case, it's this one that cannot radiate, but the duality principle, a magnetic current sheet cannot radiate on a PMC surface. And then this becomes redundant. You only need this to radiate. Okay. Are there any questions regarding this kind of argument?
Question about this GS not radiating. What's going on with the energy? If it doesn't radiate, it seems like the energy of this current is conservated.
It produces no field, so it doesn't need energy. Okay, is another thing that you might have heard about before is that something very similar to this is the case of say if I have a PEC, if I have a positive charge, the image of it is a negative charge. Okay, and then if I have a negative charge, the image of it is a positive charge. So this is like a electric dipole pointing in this direction and then electric dipole pointing in this direction. If this is a PEC surface, the image of an electric dipole is the negative of itself. Okay, so if this is JS, this is minus JS. So if you put a surface current very close to a PEC, it produces a negative image that's next to itself. So it produces no field outside. E outside is equal to 0. H is equal to 0. So it needs no energy to produce those fields, and since those fields are not there. So there's no energy involved. Can you see that? This is using a static dipole argument and assuming that it is also valid. But then using reciprocity argument, this is valid for objects of any shape, current of any shape. Okay, once it's placed on top of a PEC, it cannot radiate. But this one you can only use image theorem.
So, but if there is no energy in this current flow, it seems like it's non-existent, or I'm wrong.
The current is there, but it always produces one that's negative of itself. It means that there's no current flow. The current is canceling all the field that it generates. So it generates no field. If it generates no field, it uses no energy.
I see. Yeah, now it's clear. Thank you.
Okay, thank you then. Thank you for the question. So all these arguments that I have given you are using physical arguments with no mathematics. Okay. And some of you might not like that, and you might want to see if there's a mathematical proof for this kind of thing. There is a mathematical proof, but the proof is rather long. Okay, you can do it for Maxwell's equations. The proof is rather long. And in order to show you a proof that is similar to that for Maxwell's equation, I just work with scalar wave equations. I will just work with scalar wave equations and show that if I have a scalar field, okay, you have come across this Helmholtz wave equation before. And then if I define a Green's function for this scalar field that all of you have studied by now many times over what the Green's function is. Okay, and let me see if we can prove all these things that I'm claiming for these two scalar wave equations. Okay, and then you would not have a shred of doubt as to this is true, because when I use physical argument, you might think that I'm playing magic. Okay, I'm just doing a sleight of hand kind of argument. Okay, the English word for it is sleight of hand. Okay, and that is not satisfactory to many people. So what I'm going to do then is actually take the two equations that I have. Okay, the first one being that, and then I'm going to multiply this equation by g, the Green's function. And then I'm going to multiply the second equation by psi. Okay, just remember that because I'm going to write that on the next slide. And then I'm going to subtract the two equations. And if I subtract the two equations, then I'm going to get this equation. Okay, on the left-hand side, if I subtract them, I will get g Laplacian of psi minus psi Laplacian of g. And then I will have g k squared psi k squared g, and these two terms are subtract out to 0. Okay, on the right hand side, if I subtract them, I will get psi r delta r minus r prime. Okay, does everybody agree and see? Can you see that? Let me be more careful and say that this is, let me write the left-hand side more carefully so that you can see the arguments. So it'll be psi of r. Let me see, because I'm subtracting them, so it should be g here, g of r prime, Laplacian square of psi of r. And then because I'm subtracting them, the other term will be psi of r, Laplacian square g of r prime. And this will be true. Okay, can you see that? I'm writing it more carefully down. And,
yeah. And are they functions of frequency as well?
yeah, these are in the frequency domain. Okay, when they write an equation something like this. Okay, when they write an equation something like this, like the Helmholtz wave equation. Okay, this has to be in the frequency domain. Okay, and if I write an equation something like this has to be in the frequency domain. They don't make sense in the time domain. Okay, so everything is done in the frequency domain, and you know frequency domain techniques are very powerful. Okay, and then I want to point to the fact that this thing over here can be written as a divergence. So if you take the divergence of g grad psi minus psi grad g, okay, using the fact that if you take divergence of, say, a scalar multiplied by a vector, this would be gradient of the scalar dot with the vector plus the scalar times the divergence of a vector. This is just a product rule for the divergence operator. If you apply the product rule for the divergence operator, you can show that whatever you have here is the same as the expression above, which means that I can write this as a divergence, and then I can integrate this over the volume V that I have over here. Integrate this equation over the volume V and apply Gauss divergence theorem, okay, then I would have something like, let me put the S over here. N dot, using Gauss divergence theorem, I will have N dot G r prime gradient of psi of r minus psi of r gradient of g of r prime, okay, over the surface S. And then the right-hand side, I would have two possibilities. The possibility that when r prime is inside V, if r prime is inside V, and when they integrate over V, then this should be psi of r prime. Okay, if r prime is inside V. And it will be 0 if r prime is not in V. Can you see that? The right-hand side has two possibilities. Where do I put my r prime? If I put my r prime inside V, by the shifting property, I will pick the right-hand side up as psi of r prime. And if not, then if the delta function is outside, then I will have 0. So I have this very interesting relationship, which says that if I'm inside V, okay, if r prime is inside V, I see that the field, where did my expression go? Okay, here. Okay, if my r prime is inside V, the field inside this volume V is given by this surface integral. I should have a parenthesis here. And if I'm outside V, I have nothing. I see nothing. So this is very much like the extinction theorem that we talked about before. Which means that the original problem that I have, where I have, say, psi, let me put the original problem, I have psi of r everywhere, okay? And then I have some source. I have psi of r everywhere, okay? Can be replaced by a problem where the field is 0 outside, the field is equal to its original value inside, but I will have to put some sources. This is the same as putting sources on the surface S. And the two kinds of sources here. One is a source that radiates like this. The first one is a Green's function. Okay, this is called a monopole source. In acoustic, it would be called a monopole source because the Green's function is for an isotropic source, and sometimes called a monolayer source. The second one is actually something that looks like psi of r n dot gradient of g r prime. Okay, do you remember what the gradient of a Green's function is? The gradient of a Green's function gives you a dipole. But if you take it in the normal direction, it gives you dipoles that are normal to the surface S. So the second term corresponds to dipole layer source. So which means that if I put these sources on this surface S, okay, I can produce the same effect as I have claimed before. It will produce a 0 field outside and then the original field inside, okay? So this is the proof of this using mathematics. Okay, this is the proof of this using mathematics. And then you can actually integrate over a volume. Say if you have a source like this, you can integrate over a volume that contains both surface S and prove this theorem to be the same. And you can prove things that I have used physical argument and Canuncan experiments to prove. And you can prove using mathematics. Okay, are there any questions on this? Because I will write down the detail in the lecture notes. And the proof for the electromagnetic case is a lot trickier. Okay, then you have to write down Maxwell's equations, and then you will have to write down, say, the vector wave equation. Okay, and then you have to find the Green's function for this vector wave equation. And the Green's function for electromagnetics is not all the scalar Green's functions that you have learned before. The Green's function actually satisfies this rather complicated looking equation. It's called the dyadic Green's function. Okay. So this is the analog of these equations that you have seen for scalar wave. Okay, and then you have seen the for scalar wave, this Green's function R prime is equal to minus delta R minus R prime. When you explode it to the electromagnetic magnetic case, it explodes to something that looks like the right-hand side. And I'm sure that a lot of you are feeling very nervous about what you see on the right-hand side already. This is called a diode. Okay, and it's called the dyadic Green's function, and it has been derived before. Okay, it is given by this, multiplied by the scalar Green's function. Okay, this is called the dyadic Green's function. Okay, and you can prove by back substitution that when you plug this equation back here, this equation is satisfied. Do you know what the diode is? Does anybody know what a diode is?
Is it just a matrix?
It's a kind of matrix, you're right. It's a tensor. Okay, it's a tensor, a second rank tensor. And a diode is also when you put two vectors, A and B. In physics, you just put them like that. In linear algebra, you will have written them like A, B transpose. Okay, so a diode is just two outer product between two vectors. So you can think of this as outer product. Okay, this is outer product, and this is identity diode. And you can actually plug this in and go through the math. The math is rather complicated, but I've written it up in the lecture notes. Okay, let me just show you part of the results of the lecture notes. And I'm not going to derive them because the derivation is rather long, but very similar to the scalar wave case, that if you have this problem, then you will have the electric field is either zero or non-zero, and it's given by the surface integration of a closed surface, and then n cross E, which is some sort of a magnetic current sheet times the curl of the dyadic Green's function plus I omega mu n cross H R dot G of R prime. Okay, so this is the dyadic Green's function case, and this is the electromagnetic case. But actually, it is homomorphic to the scalar case, which means that whatever you see in the scalar wave case, you also see in the vector case. Like if you look at the scalar wave case, you see something like this. Okay, there are two scenarios on the right-hand side. You have this thing over here, but then the expressions are a lot more complicated because you have to deal with vectors and diodes. And you can also have extinction theorem. And this part is just extinction theorem. Okay. So I'll stop here and entertain any questions that you might have. Okay. Does anybody have any questions? Okay, if you don't have questions, like you have to think about this quite a bit, and you can go and read the lecture notes to have a better grasp on this subject matter. It's interesting. And if you understand this subject matter, it can help you a lot in your future, because the half-life of this knowledge is quite long. And if you have this sink into your soul or sink into your brain, you can keep inside you for a long time. Okay? Any questions? If not, I'll let you go, and thank you for coming.
Thank you, Professor Chu.
Okay, thank you. Bye-bye.
Thank you.